make sure we get it like
Is the board true?
Yeah. All right, so here we go. Yesterday we were talking about asymptotes. Okay, we're talking about the idea that when we graph something like y equals 1 over x, okay, there is an asymptote at x equals 0 because I'm not allowed to divide by 0, correct? When we started, I think the bell rang when we were talking about this, but we were talking about how if you were to place your finger, let's say your finger is point A there, and on your left hand, and on your right hand, point B. Let me see if I can get this to show those a little bit larger. Menu font.
Put stock in Amazon.
I have exact.
Yeah.
I did Amazon, Google.
Wait, how much did you get to put stock?
Okay. So if you're putting your finger at point A, and if we look at the x values here, the x values are going to be moving towards 0. Does that make sense? These x values here are moving towards 0 from the left. Is that okay with everybody?
Yes.
And as my x values approach 0 from the left, we see the behavior in our y. Our y value is getting more and more negative, right? If I put my right hand on B and I start moving it towards 0, so it's approaching these x values here are approaching 0 from the right hand side, those y values are going up to positive infinity, right? So because they go to different values, because A goes to a different value in terms of the y, and so does B, we would say that we have discontinuity here. The points diverge from one another, okay? And that is then symbolic of the asymptote, meaning that we knew that we could not divide by 0. We cannot cross this, so there should not be a point identified on that red line, okay? Every time that you come in contact, I don't want to say contact, in relation to a asymptote, your graph is going to do one of two things. It is either going to, from either direction, it's going to either go to positive infinity or it's going to go to negative infinity. Because what happens algebraically, and we'll see some of this in examples, is that ultimately when you plug in a number like, in this case, 0.0001, you're dividing a large number, like 1, by a very, very small number. If I take 1 and divide it by something that is 1/1000th or 1/100,000th of its size, that quotient becomes very large. Does that make sense? Yes. Okay. And if one of them is positive, obviously then the quotient is positive. If one of them is negative, the quotient is negative. So that's what's going on here at this asymptote, and it's what happens at all asymptotes that are vertical. Okay. You end up dividing a large number by a very, 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 very small one. And we have got positive and negative aspects that make it go up or down. If we were to look at something like, just to continue talking about that idea of converging and diverging, if I look at like the value of x equals 2. Now I'm putting a line there, but obviously there shouldn't be a line for this graph. I just want you guys to focus on this x value of 2. Would you guys agree that if I look at this point A, put that back in. If I look at this value A, or this point A, would you guys agree that the x values are approaching 2 from the right-hand side? Okay. Would you guys agree that B is approaching the x value of 2 from the left-hand side? Okay. Look at the y values. Are these y values for A and B, as we move closer and closer to 2, are those values of A and B for the y's, are they getting closer and closer to one another? Okay. So that idea then is because as we, and I shouldn't actually click right on there because the idea is that there could actually be a hole there. But these y values, as x is approaching 2 from the left, and as x is approaching 2 from the right, you're getting the same y values eventually, right? So because of that, that's actually what we refer to as the definition of a limit. Meaning that that point right there is defined on this curve. Meaning at that point of 2, our curve is continuous. Does that make sense? Okay. Now, in order for the entire curve to be continuous, you then need to do that at 2.00000000001. You gotta do it right to the next real number right next to 2. And then you gotta do it for the next real number right next to that. Does that make sense? And you should be able to, if you get this result where when the x's approach that real value from either side, and they both approach the same y value then, that means that each one of those points is defined and it makes a continuous graph. Okay, there's no holes or gaps. That doesn't happen here at this red line. Okay, so overall, this graph is not continuous because we have asymptote discontinuity right here. Okay, which is algebraically the division by 0 concept. Does that kind of make sense to everybody? Yes. Yes. I want to do one example of a transformation and how transformations can be used in rational functions. If we understand what 1 over x looks like, we should be able to use transformations with that. If we know what 1 over x squared looks like, which is another rational function, 1 over x squared is going to be basically both branches. So this branch here is going to be reflected up into the second quadrant. So if I look at 1 divided by x squared, gives me that. Okay. If I know what 1 over x looks like, I know what 1 over x squared looks like. Then I should also know what 1 over x cubed looks like. Let's look at 1 over x cubed real quick. Good. You're going to hear more of it. 1 over x cubed looks a lot like 1 over x, right? Okay, now the kind of the rate of increase or rate of decrease on this is a little bit faster than what it was on 1 over x because of that cubic in the bottom. If we understand those, which I'm not going to require you to, you could use transformations to graph all of our rational functions. Okay, and I'm going to demonstrate it with 1 over x. But what we eventually learn, what I think is easier, is just a kind of systematic approach to every rational function. We'll find asymptotes, we'll find vertical and horizontal asymptotes, we'll find x-intercepts, y-intercepts, and then we'll do test points. And that'll give us enough to graph our functions, where I think that's more efficient than trying to do these transformations for 1 over x, 1 over x squared, 1 over x cubed.
So is discontinuity when they're approaching 0, they end up going opposite ways, and continuity, they end up going the same way?
No, so these would still be, the 1 over x squared would still be discontinuous because there's still an asymptote there. And it's the idea because that one involves going to like infinity. Like it's easier to explain when you have more calculus on your belt, but it's because they're both going to infinity, and that's just an issue. Is your question?
So when you're talking about the limit, so if 2 was a whole, then would it be the limits if both numbers are approaching 2 in the graph you're talking about?
Well, there could be a hole there. So if they're still both approaching the x value of 2, the y value would still be because one would be like 5.000000001, and the other would be like 0.499999999. Those are still both approaching 0.5. So we would still say that there's a limit there. But then there's added stuff to determine in continuity, but that's basically the main foundation of it. That stuff will make a whole lot more sense. We can still go off the idea that continuity is tracing it with our finger. The limit stuff will make more sense next year after we talk about actually defining a limit with graphical and algebraic approaches. Does that make sense? Okay, so this one here. So I want to look at 1 over x. So this is a transformation problem, which is a tool that we have at our disposal. We can use this if we want to. I'm going to remind myself that y equals 1 over x. There's a series of points on there, and they're easy to determine, that we should kind of commit to memory. 1 over 1. If x is 2, we got 2 comma 1/2. And if x is 1/2, we have a y value of 2. Does that make sense?
Nobody. Which
What's up?
one of these did I just fix for you?
This one.
This one?
Yep.
Okay. Everything okay?
Yeah, it's working good.
All right. Gotta put this on here. Try not to let that fall off. It's a little sticker.
All right, cool. Thank you. So then we've also got, so that would be that branch that was up here. Okay? The branch that would be down here is a 180-degree rotation around the origin. Okay, so this thing has y-axis and x-axis reflections or symmetries. So basically what that means is if 1, 1 was on it, -1, -1 is on it. If -2, 1/2 was on it, -2, -1/2 is on it. And then the same thing for that one. Does that kind of make sense? So those are, obviously, I only remember 3 of those points, and I really don't remember them. I just evaluate them real quick. The 1, 1, 2 over 1/2, or 2 comma 1/2, and 1/2 comma 2. And then knowing that there's a reflection there, or a symmetry about the origin, or rotation about the origin, can allow me to find those other 3. Okay. Now, if I understand that for the parent function, that's the parent function, the reciprocal function, we should be able to graph this knowing that information. Okay. And this is how we do this. We have to transform this algebraically. And this one's not too hard to do. But we have to transform this one algebraically so that we see something that resembles 1 over x. So what I'm going to do, I need a 1 in my numerator. And then I'm going to factor out a 2. Does that make sense? So factor out 2. And I'm left with 1 over x minus 3. So this here models that there. Okay. However, I am subtracting 3 from the x. In all our transformations that we've ever done, when you subtract from the x, which way does that move the graph? It moves it right 3 units, right? In all of the transformations we've done, if we've got a number out front, what does that number out front do to the entire graph? Stretches, it's a vertical stretch, right? And it's by a factor of 2. Okay, so if we've got these ordered pairs, Control C, Control V. If these were the ordered pairs on our parent function, why won't it let me grab those? There we go. All right, so if those are our, just bear with me, computer's being stupid. All right, so these were the parent functions. So what we're going to do is we're going to move them right 3 units, and we're going to stretch them by 2. So if I'm going to move this right 3 units, doesn't that value become 4? That would move right 3 units becomes 5. And this one becomes 7/2, 3.5. Is it okay with everybody? I'm going to move these all 3 units to the right. So it becomes 2 comma whatever. Move that one 3 units to the right, so it becomes a 1. Move that one 3 units to the right. So it becomes 5 halves, 2.5. Okay, so that's what the horizontal shift did. The vertical stretch takes each one of these y values, and in this case, doubles it, right? So that y value of 1 becomes a y value of 2. This y value of 1/2 becomes a y value of 1. This one of 2 becomes 4. Over here becomes -2, -1, -4. And now if we graph these points here, they should be the transformation of 1 over x, 3 units to the right, stretched by a multiple of 2. So take a minute and graph those. We got 4, 2, 5, 1, 7 halves, 4, 2, -2, 1, -1, 5 halves, -4. Okay. So it's those points there, correct? Do those points, do they match y equals 2 divided by x minus 3? That makes sense to everybody how we can do that with transformations? Okay. Now, like I said, I think what we're going to start discussing here in a moment is going to be maybe a more complete process for graphing these. Okay. What can I not divide by here? Okay, so x cannot be 3, right? Okay, is that a vertical asymptote? When it was a vertical asymptote for 1 over x, it was at 0, right? So even this x minus 3 moves everything. It moves asymptotes and it moves the curve. Okay. So that is one technique that you can use to, like I said, graph rational functions. But when we get down to something like graphing one of these things here, that process is not as convenient, okay? However, the process that we learn here, okay, with graphing these will work and will actually be faster than graphing this one using the technique we just learned. Does that make sense? So I want to go through this more complete, more wholesome procedure, and that will allow us to graph everything that is a rational function. All right, so what I want to talk about today is a understanding of what our asymptotes look like and how we generate them per question, okay, per rational function. We'll start with the horizontal asymptotes, okay? Then tomorrow we will hopefully finish talking about them and then introduce vertical asymptotes. And once we have those two concepts understood, then it's just a matter of finding x and y intercepts, which should be easy once we have things factored, and collectively putting all that stuff together in a graph. Okay. The one thing about, in discussion of what our asymptotes are for a rational function, the horizontal asymptotes, I could give you just this rule here. I could give you these three things and say, those are your asymptotes and those are always your asymptotes, and there's never anything that contradicts those, which would be fine. And I could say, you guys just do that. Okay, just do those three things and you'll be good. But I think what you find out is you don't necessarily understand maybe why these things originate this way or they're set up this way. And when we get to a test or a quiz, we might, because if you look at these three conditions and these hypotheses, those three things I just highlighted are very similar, right? And it would be very easy for you to confuse them and maybe put this one here, this conclusion, down here instead. Does that make sense? So I just want to make sure we understand algebraically why these three scenarios play out the way they do. Okay, so it's all about division. It's all about quotients. okay? And an understanding that when we look at a horizontal asymptote, we don't really care what the asymptote or what the graph is doing near the asymptote when x is relatively small. We care what it's doing near the asymptote when x is really, 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 really big in either the positive or negative directions, okay? So that's what we're talking about. We're talking about the behavior of a rational function near its vertical and horizontal asymptotes. Like I said, in this case, the horizontal one, and that is only when x becomes very large, okay? So here's some of the algebra. I'm just going to grab one of these functions down here. We'll do, I think in the last class, I did that bottom one, so I'll stick with that one. Okay, taskbar. All right, so the first concept here is you're going to let your rational function be of this format, where you got a polynomial at top and you got a polynomial on the bottom. Okay, this is the generic polynomial format that we've seen in the past. The one on the bottom is identical, except for using b instead of a and m instead of n, so we can differentiate and talk about the top and the bottom easier. What we're going to find out is that that one there, or that term, bad color to choose, that term and that term dictate 100% of the time what your horizontal asymptote is. Okay? Those are your leading terms, right? Okay? All of these other things are negligible. Okay? When x becomes really, really big. And we've talked about this before, but I want to reiterate it because I think it's important for us to see and hopefully be able to justify to ourselves. If I look at that function right there, what I want to do is I want to take this top one and recognize the leading degree, the leading term, and I'm going to factor that leading term out of the numerator. And when we factor out, that's just effectively doing division, right? Now, this would not be something you do on every one of these problems, because if we could do this once, we can justify that it happens all the time, and then you can make these shortcuts that are presented in that theorem, that blue box I was showing you. If I look at the bottom, I want to factor out the leading term again. So it'll be 4x cubed, minus then 3x squared over 4x cubed, minus then x over 4x cubed. Okay, so if we do that, what do these terms reduce to? What's this term right here reduce to? 1. Okay, so I'll have 3x cubed. I'll have a 1 there. Now this is going to be plus the x squared and the x to the third. They cancel and leave me, what, 4 over 3x? And then in this last one, the 3's cancel. And leaves me 1 over x cubed. Is it okay? And then we'll do the same thing with the bottom. With the bottom, this one here turns into a 1, so I'll have 4x cubed, then a 1, and then these x squareds cancel down there, so I'll have minus 3 over 4x, and now this x will cancel with one of these x's, leave me 2, so I'll have minus 1 over 4x squared. Everybody okay with that? What is that doing for me? Let's think about this. Let's say that I have, let's just type in one of these. Let's just go 4 over 3x. But I'm going to use 4 over 3a. And I'm going to let a be a slider that goes from, let's just say 1 up to, I don't know how far it'll let me go here. So what's that? Trillion. Okay. As I do this and I start to evaluate as A starts moving, what does this number here get closer and closer to? Yeah, it's getting closer and closer to 0, right? Okay. You can look at the number, even completely neglect the scientific notation right now. Just look at this number here. Is that number getting eventually smaller and smaller, closer and closer to 0 itself, right? Okay. And now if I incorporate the 11 zeros before that 1, you can see that's getting very, very close to 0 as x gets big, right? Now, if I was able to let this thing go to even larger values, you can see then that now we get to negative 21 as my exponent. So now we've got 20 zeros, okay, which is a much smaller number, closer to 0 than it was when it was 11 zeros out front, right? So what does that mean for us? What does that tell us that this number, when x, because we're interested, remember, in behavior, the horizontal asymptote is just for when x gets really, really big. So when x gets really, really big, doesn't that quotient right there end up being 0? Does that make sense, everybody? And this one here is going to be the same thing. It just happens a lot faster. Because instead of 4 over 3a, now you have 1 over a cubed. Well, that a cubed is going to grow much faster than 3a. Okay, so you'll get to 0 with this one much quicker than you got there. But they both go to 0. Same thing down here on the bottom. That goes to 0, and that goes to 0 when x is really big. So what does that mean to us? That means that on the top, we really have 3x cubed, and that stuff is going to go to 1, right? 1 plus 0 minus 0. Just 1. So you have 3x cubed times 1. On the bottom, you have the same thing. You have 4x cubed, and then you got 1 minus 0 minus 0. Well, that's just 1. So this thing here is 1 times the 4x cubed. So that's what you have right there so far when x gets really, 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 really big, right? Does that make sense? Well, when x is really, 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 really big, let's say x is 1 billion, then when I take 1 billion, which has got 9 zeros, and I cube it, that turns into 27 zeros, right? Well, do I have a 1 with 27 zeros up top and then a 1 with 27 zeros on the bottom when I choose x to be a billion? That makes sense? So when x is really, really big, and then whenever x is any number, does this, I know why it keeps doing that. There we go. Whatever value of x is, and like I said, we're really interested when it's really big, but doesn't that and that cancel each other out? And what are you left with? 3/4. And the idea then is if we were to use a very, 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 very large number of x, a very, very large number of x, and we plug it in here, okay, for every x that is in that rational function, if you choose a really, 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 really big number, as big as you can get, it's going to evaluate to 3/4. Does that make sense? Okay, because those other components are negligible. This amount here and that amount there are negligible compared to what this does. So that is the reason why they say when, and it's option or component B here for this theorem, says if n is equal to m, if your leading degrees of both the top and bottom functions are the same, then you have a horizontal asymptote at the coefficients divided by one another. Okay, so if we take the functions that we just messed around with, 3x cubed plus 4x squared minus 3, and 4x cubed minus 3x squared minus x, and we divide them f divided by g. Okay, so we're interested right now in eventually graphing this gray function. Okay, if I want to graph that gray function, one of the key things that we're going to do is first have to find the horizontal asymptote. Well, right now, because these degrees are the same, and through the algebra we just went through, the horizontal asymptote should be at 3/4. So I'm gonna type y equals 3/4 in. Would you guys agree that that red line behaves as a horizontal asymptote? As we move in the positive x direction, is our gray graph getting sucked towards that red line? So it plays as an asymptote in the long run. Does the same thing happen in this direction? Okay. Now we cross it twice in this case. You can cross a horizontal asymptote, and we said yesterday if that does happen, it will usually happen relatively close to 0, 0. And these spots where we cross are pretty close to 0, 0. There will be some algebra that we go through to determine that. If I were to flip it, so we did f divided by g, let's do g divided by f. Okay, so now if the leading degrees, they're still the same, they're still both x cubed, where should the horizontal asymptote be now? 4/3. So if I type in 4 divided by 3, we see that in the long run, that graph does approach those horizontal asymptotes. Okay. One thing, and we'll pick up here tomorrow, but the next thing is what happens when the numerator's degree is less than the denominator's. When the numerator's degree is less than the denominator's. Well, think about this here real quick. If I take, let's say if this one was a 4th degree right there, then this would be a 4th degree right there. Does that make sense? This would be a 4th over 4th. All of these would be one more power in the bottom. So what's going to happen is that over here, this would be like x squared instead of x to the first. And this here would be x to the third instead of x squared, right? Do they still go to 0? These still go to 0. This still goes to 1. So I'm still only looking at my leading degrees or my leading terms, right? But now my leading terms are this. 3x to the third over 4x to the fourth. Do the x to the thirds and the x to the fourths cancel to some degree? Does it leave me that right there? So now what happens when x becomes really big? You have 3 divided by a really big number. What's 3 divided by a really big number? Really small, getting closer and closer to what? 0. So when your leading degrees, when the bottom degree, and that's what this one here is saying, when the bottom degree is bigger, so when that m is larger than that n, you are always 100% of the time going to have a horizontal asymptote of y equals 0. Okay? That's because when you do the cancellations, you're always going to be left with a variable component in the denominator, and that makes a integer divided by a very, very large number, which is 0. See ya.